In this video, we're going to take a look at electrophilic aromatic substitution reactions of heteroaromatic compounds. And when we do so, we see that the heteroatom, nitrogen or oxygen, introduces a little bit of complication. And the main reason for this is because not all of the carbons are now equivalent. If we take a look at pyridine reacting with some electrophile, and we think about what types of substitution reactions can take place, we can number the pyridine starting at the nitrogen, where the nitrogen gets 1, and then we kind of follow all the way around, 1, 2, 3, 4, 5, 6. So let's think about the possible substitution reactions that can occur. Nitrogen never gets substituted, so only carbons are going to undergo substitution, because if the nitrogen does, then aromaticity is lost. So we could get an electrophile adding to the 2 position. We could get an electrophile adding to the 3 position, or we could get an electrophile adding to the 4 position. Of course, adding to the 5th position, there's symmetry with carbon number 3, and so it would give you the same product. So all in all, we see that there are 3 possibilities for electrophilic aromatic substitution. And so the question then becomes, well, is one position favored over the other? In order to determine this, we have to think about the intermediates of these reactions and to see if in a certain position intermediates are stabilized over other positions, like we saw in the previous section. So let's take a look at the substitution at the 2 position. Again, this is electrophilic aromatic substitution, so the pyridine in this case is the nucleophile. It's reacting with an electrophile. We see donation of electron density from the pi bond to the electrophile, and our intermediate carbocation looks like this, right? If the electrophile adds to the 2 position, there's a carbocation on the 3 position. And of course, we have resonance stabilization, so we can donate a pair of electrons from the pi bond to that carbocation. We generate a new carbocation that would now be at the 5 position. And of course, you can see we can now write a new resonance structure from this, donating a pair of pi electrons again, and we end up with a well, this is not a carbocation, it is a nitrogen cation, right? And if we think about the stability between a carbocation and a nitrogen cation, we see that carbon is more electropositive, nitrogen more electronegative, and so the stability of a positive charge on the nitrogen is not going to be very favorable relative to that on a carbon. And so we say this is a bad resonance structure. If we look at substitution at the 3 position, again, the pyridine is going to be a nucleophile. Pi electrons attack the electrophile. We generate now this carbocation, cation. It's a carbocation. It's not a cyclohexadienyl carbocation, but a carbocation nonetheless. And now the carbocation is on the 2 position instead of the 3 position. So notice I used the same pair of pi electrons, but instead of placing the electrophile on the 2 position, I'm placing it on the 3 position, and the carbocation goes on the 2 position. Now, thinking about resonance structures of this, again, I can donate a pair of pi electrons, adjacent pi electrons, to that carbocation, and I generate another carbocation where now that that ion is on the carbon number 6. Carbon number 6. And another resonance structure where the carbocation is now placed on carbon number 4. And so you see that we still have 3 resonance structures, but the positive charge never goes on to the nitrogen. And um, so obviously this is a good thing relative to that of substitution at the 2 position. Now, if we look at the 4 position substitution, you should have some type of inkling, some type of chemical common sense that might tell you that we're going to see a similar pattern with a substitution at the 2 position. And yet we should never go by our gut, right? Thinking about how we get an electrophile on the 4 position, we take a pair of pi electrons between C4 and C5, and we generate again this carbocation where the positive charge is on C5. Now notice when I draw a resonance structure of this, donating a pair of pi electrons, I generate that cation again where the positive charge is on the nitrogen. And of course there's still that 3rd resonance structure where the carbocation is on C3. So here we see, just like when you get substitution at the 2 position, substitution at the 4 position leads to a cation on the nitrogen. So the nitrogen's electron deficient relative to a carbon being electron deficient, and this is bad, right? So 3 position substitution should be favored over both 2 and 4 position substitution. And indeed we can look at a bromination of pyridine. So if I take pyridine and react it with bromine in the presence of aluminum chloride, I get that 3-bromopyridine in a 90% yield. Now, having said this, this reaction is very slow relative to the reactions of benzene. And the reason for this is because it's not quite, pyridine is not quite as nucleophilic as that of benzene. All right, so we saw other types of heterocyclic aromatic compounds, and one of those is pyrrole. If you recall, the structure of pyrrole looks like this, right? So it's a 5-membered heterocyclic compound. Nitrogen's in the ring. Nitrogen has a hydrogen coming off of it, a pair of electrons, and of course we know those pair of electrons are part of the aromatic system. And so when we think about substitution on pyrrole, again we can number the ring where the nitrogen is number 1, and then we go around 2, 3, 4, 5. So we have 5 atoms. And thinking about substitution, electrophilic aromatic substitution, we see that the electrophile can either go on the 2 position or the 3 position. Of course, putting it on the 4 position would be the same as putting it on the 3 position, and putting it on the 5 position is the same as putting it on the 2 position. So in this particular scenario, we only get 2 possible substitution products. Again, thinking about which one of them is going to be favored, we have to look at the stability of the intermediates, the intermediate cations. So I'm reacting pyrrole with an electrophile. Again, pair of pi electrons attacks the electrophile. I generate my carbocation, which by now you should be very accustomed to drawing carbocations of aromatic compounds. So I get the carbocation here. Notice the plus charge is on C3, and I can draw a resonance structure of this, right? Donating a pair of pi electrons, and I get the carbocation now at C5. And I see that I can now draw another resonance structure, taking that pair of electrons from nitrogen, donating it into the ring, and I get a positive charge on the nitrogen. All right, so in in one scenario, we see that this is bad, and with pyridine, we saw placing a positive charge on the nitrogen is bad, and so uh, in the 3 position, it can be avoided, and we saw there were 3 resonance structures that avoided the positive charge on the nitrogen. With pyrrole, we see that the nitrogen can't be avoided at the 2 position. Well, let's take a look at the 3 position. So when we substitute at the 3 position, pyrrole reacts with that electrophile, again a pair of pi electrons, but now the electrophile is going to go on the C3 and the carbocation goes on C2. But notice this time I have a resonance structure also of this, but it also involves the nitrogen. So I donate that pair of electrons from nitrogen and I get this resonance structure. Notice I can't draw another resonance structure. So for both the 2 position and the 3 position, nitrogen gets involved in stabilizing the cationic intermediate, but in the 3 position, I can only generate 2 resonance structures. And so this is important because for the 2 substitution at the 2 position, I can generate 3 resonance structures. For the substitution at the 3 position, I can only generate 2 resonance structures. And therefore, the 2 position substitution is going to be favored due to that extra resonance structure to help stabilize that cation. And indeed, we can see this when I take pyrrole and I react it with nitric acid in acetic anhydride. I do get both products forming, right? So 2 nitropyrrole and 3 nitropyrrole, but the 2 nitropyrrole is highly favored at 80% product distribution versus 20% of the 3 nitropyrrole. And of course, we can look at reactions of furan and thiophene as well, right? Furan is very similar to pyrrole, except instead of nitrogen, you have oxygen as part of that heteroaromatic ring system. We see when furan reacts with chlorine, we get that 2-chlorofuran. So substitution is occurring at the 2 position, just like it's favored in pyrroles. Likewise, with thiophene, we can do electrophilic aromatic substitutions of thiophene as well. So here I have Friedel-Crafts acylation, and we see that acyl group goes again on the 2 position. So for furan and thiophene, reactions also favor the 2 position. And the reasons for this are very similar to the reasons of stabilization of those intermediates with the pyrrole that we saw. Now, we also notice that with furan and thiophene, these heteroaromatic compounds are very reactive toward electrophilic aromatic substitution reactions.